Okay, so let's discuss first what is low no slip condition. As we know that liquid is always confined with solid boundaries, and it is oftenly come in the contact with the solid walls as well. So there is a condition at which we so called as no slip condition. So for demonstrating this phenomena, I one use this figure as well to easily demonstrate you. Let's suppose a liquid is flowing over a solid surface, which is so called, as you may say, as a plate or a solid boundary. So the liquid is flowing in this direction. If we draw the velocity vectors for each layers, as we have discussed in the previous lecture, that liquid always flow in the form of layers. So we can see here the velocities vectors here from highest point to this point has almost equal velocity, but below than this point you can see here the velocity is gradually decreasing and decreasing and decreasing to the zero mark. If the plate is at a stationary condition, obviously the layer which is very adjacent to the surface will get the velocity of 0. If this plate has a certain velocity, then this layer has the same velocity as the solid surface has the velocity. So the matter is that the certain layers are attached with the solid surface and do not slip at all with this wall. So it is like that if you have a bowl full of water and you dip your finger on them and just take out from the water. So definitely you have certain water in your finger, and the layers which is attached with your fingers are so called as, due to no slip condition, they are attached with your finger. Okay, this is something which I have described you as a liquid flowing on a solid surface. But let's suppose if the liquid is flowing and it is flowing over a curved surface or solid wall surface. Okay, this is a smooth straight surface. This is something we can say the liquid is flowing over this. Okay, later on we will discuss about what is internal flows and external flow, so you will definitely easily differentiate what is flow over the surface and internal flow them. Okay, so let's suppose if we have a solid surface and the liquid is flowing over this with a low velocity. If the velocity is very low, then this point you can't be differentiate. Okay, it is moving with this in a manner that it will fill up all these layers. But if we increase our velocity up to a very higher mark, so what happened, it contain a very sharp point at which the liquid layers are separating the solid surface. Okay, so this point is so called as the separation point. Let's consider an example or a case in which there is water is a wire. Okay, and it is allowed to flow down this solid surface. Okay, what happened? The water is filled up to that mark, and it is flowing in this direction along this solid surface, which has a velocity of 0. Okay, so if we draw similarly, what are the velocity vectors of the each layers of the liquid? So we will come to know that it is forming a velocity profile of in this manner, in such a way that the topmost layer has the highest velocity, and then in next to it has a very minor low velocity, and this velocity is gradually decreasing, which so called as the velocity gradient. Velocity gradient is, if we say this is delta y, and we are saying this as delta v. So which velocity gradient can be defined as this. So we've come across with this type of velocity gradient behavior of the fluid. But the most important thing is that the layer which is very adjacent to this is stuck with the solid wall and has the same velocity as the solid wall has. So this is so called as that it is just struck in the on the surface of the solid wall, and did not sliding at all on from this. So we can say that this is no slip condition. Where layer has 0 velocity. Let's consider another case. Okay, as liquid flow in different patterns. This is an open channel flow. Okay, if we consider a flow of an internal pipe which is confined by two solid surface, like this is one solid surface and this is another solid surface, and this pipeline has this shape. Okay, and the liquid is flowing internally on this surface. So it has a velocity profile in that manner. Here definitely the middle one layer has the highest velocity. We can say the V here is V max. Although if we go above to this layer or lower to this layer, the velocity gradually decreases and decreases and decreases in such a manner that when it reaches to the solid surface, it becomes 0 in both pattern. So again, this is just stuck with the solid wall and unable to move at all. So we can say here this point to this point, this has no slip condition. And this is both have same no slip condition. And it depends upon the type of fluid. If the fluid is much viscous, so the thickness of this layer must be greater. If the liquid is less thick viscous, then it has very thin layer. Okay, so let's consider another case. Let's suppose the motion of submarine. The submarine run under the sea in certain manner. Let's suppose this is certain part of the sea. We have conduct, okay, and This is the submarine present here. Which is moving. The liquid is flowing and coming on the surface of this solid boundary. And there, if we develop how the layer behaving after striking with the solid wall, let's suppose we have made it in a separate diagram. Okay, the liquid come, strike and attach with this and move on. And after certain height, there is not a very huge change you will see due to the solid surface. Okay, their directions, their layer will not form any type of deformation of like they do not curve out, they do not show any rotational flow or eddies formation. Again, here you will see definitely all the layers are attached here and has no slip condition. But let's suppose the velocity of water becomes increased, or the solid boundary, the solid submarine which is moving in the forward direction, increase its velocity. So what happened? After a certain point, this phenomena does not move in that manner. Okay, so definitely there is the solid no slip condition, but the layers here when the velocity was lower in the magnitude, they filled up all these things and move in a particular direction. But when the velocity increase and increase and increase, there is a point come when the layer which is very adjacent to the solid wall shows some separation, which is so called flow separation. Okay, another thing is that which in the previous lecture I have discussed about how the heat exchanger work. So I just I think I move forward to the video. Okay, let's consider another case in which the double pipe heat exchanger. Okay, which has some geometry like this. Okay, this is the upper surface. This is the inner part. Let's suppose we have an exchanger. Okay, this is the inner pipe, and this is the jacketed pipe. Okay, a fluid is coming, entering from this part in that way. Okay, has a velocity profile like this. On the other hand, the jacketed fluid is coming in this way. Okay, that it has velocity profile like this, and they are moving counter currently to exchange their energies. Okay, so one is getting heat up and second is getting colder and colder. But here again, due to no slip condition, this is the solid valve, this is the solid wall. Okay, and again this is the solid wall. The liquid here definitely attached with this solid wall and has velocity equals to 0. And due to this, getting the velocity equals to the solid wall, it's again retain its position with the solid wall, and due to which it's if we see the temperature of wall becomes equals to the temperature of the boundary layer. Boundary layer is the layer which is attached with this solid surface. Okay, so this phenomena is also called as no temperature, as I have discussed here in no temperature jump condition. Okay, so this condition is called as no temperature jump condition. Because this is no slip condition here, the liquid definitely attached with the solid wall, and it can't be moved from this wall. So the temperature that wall attains at certain time or at a particular condition, so the liquid layer which is attached with the solid wall has the same temperature. So this phenomena is also called as no slip or no temperature jump condition. Sorry. So these are the diagram which is showing this is the boundary layer of the liquid, and when the liquid is flowing over the solid surface at a very high speed, there is a separation point at which here is the boundary layer is much thicker, but it getting thinner because of the high velocity, and it separate out certain part from the boundary layer to the liquid part, and will not retain its position with the solid wall. Okay, then we move towards classification of fluid flow. Actually, it is important to classify the cases because different scenario has different law to apply, and it makes simpler to understand when you classify things, so you know which condition is applicable for certain case. So considering all these things, we can classify the fluid flow in numerous manners, in which the viscous or inviscid flow region, internal versus external flow, compressible versus incompressible flow, laminar versus turbulent flow, natural flow versus forced flow, and steady versus unsteady flow, or the last one is 1, 2, or 3 dimensional flow. Okay, let's move forward to the viscous versus inviscid flow region. Okay, this is not a very complicated thing. It is also associated similar like what we have studied, like no slip condition. Let's suppose we take a diagram here. Let the liquid is flowing over a solid surface. And it has the velocity profile like this. The topmost layer of the liquid has the highest velocity, and this is the boundary layer, which has velocity equals to 0 meter per second squared. Okay, so if we see beyond this layer, the flow pattern is like this. So we can differentiate here. There are two regions, one where the velocity is almost equal, and the other region where the velocity is changing so rapidly. Their magnitude has a very high differences in their magnitude. Like if we differentiate here from this part to this part, the velocity gradient is not much greater, you can see. And here the velocity change along the vertical direction is much greater in amount. So we can say that there are two regions. One is the inviscid region, and the second is the viscous flow. Here I just want to recall you what is viscosity actually. Viscosity is the property of the fluid that resists to flow. So as we can see here in the diagram that the layers are moving in a certain direction over their surfaces, but here the layer has the same velocity as this layer, and this layer, which has a very minor change in the velocity, which shows that at this particular part the viscosity has not a very great effect at all. Less viscosity effect. Region. On the other hand, if we see here, this layer restricting this layer, due to which this layer comparatively has low velocity than the preceding layer of the liquid. And similarly, this layer also resisting this layer to move faster than this layer, and the boundary layer again resisting the upper layer to move in with the higher velocity. So again, we can see here the resistance which is offered by the liquid for flow, which is expressed by the phenomenon of viscosity, is much effective in this region as compared to this region. So that's why we can categorize the flow in two types of region. One is inviscid region and the second is the viscous flow region. The viscous flow region is the region at which the viscosity has a greater impact, but inviscid is you can say the region where viscosity does not affecting the flow at all. So this is the main difference between these two. Here again, the difference between these two things is also described by this diagram. Okay, what happened? The liquid is flowing all around it, and we have placed a simple solid rod here. You can see where I am pointing the mouse. So in these two parts, from this boundary layer to this layer, we can see the velocity gradient is much higher, and above to this part there is not a very great, even almost all the layers has the same velocity, so which can be categorized as inviscid flow region, and this part may categorize as the viscous flow region. Similarly, on the bottom face, this is the upper face of the plate and this is the bottom face of the plate. So again we have a boundary layer here. All these things, like this is the no slip condition. Then we can see here from this part to this upper part, the velocity gradient is much higher, and lower to this part we are unable to see any greater velocity changing in the flow pattern. So again we can categorize the flow into two categories, like one is the viscous flow region and the second is inviscid flow region. Now move forward to the internal versus external flow. So as I have described you both the cases, one is the in the previous case, like there is a water reservoir and the liquid is flowing down to that, and the second is the submarine is moving in the sea. So when the submarine is moving the sea, the flow of the liquid is coming outside of the wall of the water solid surface and is striking it, maintaining a boundary condition as well, boundary layer as well, no slip condition as well. But that part of the flow we can categorize as external flow. Okay, and the flow which normally happen in the duct or in pipeline is so called as come in the category of the internal flow. So these are the two basic definition of internal and external flow. Although internal flow, there is another category like open channel flow, like the reverse flow, or I have given you the example of water reservoir and the liquid is flowing down the along the over the surface of the solid plate. So all these things come in the category of open channel flow. Here you can easily understand, this is a very good example of internal flow and external flow. Both simultaneously. Like this is the pipe here placed, and there is a liquid which is flowing inside this pipe. This category of flow we can categorize as internal flow, although if this pipeline plays in such a manner that the liquid is and that the fluid is flowing over the surface of the pipe and move so on. So this category we can categorize as the external flow. This diagram is also showing the internal flow, and on the other hand this ball present in the way of the liquid or a fluid or a gas, showing the external flow pattern. Then we have a compressible versus incompressible flow. Basically we must need to understand on the which behalf we say that this fluid is compressible and this fluid is incompressible fluid. So the basic definition is that if the fluid is moving and from one part to another part, or going through under certain change in the conditions of temperature, pressure, and these type of variables, and after that it is not show too much variation in the density, then we can categorize it as a incompressible fluid. But if we come to see a density change over a particular range of the volume which we are observing, so that come in the category of incompressible fluid. So now it depends upon which type of flow we are observing. Like it is not necessary that gas or air always be considered as compressible flow or compressible fluid. Definitely it is compressible, but if we are observing a particular case, or we have a particular scenario in which the inner part to outer part, or maybe at the middle part, we have some variation in the process, but we are unable to see a very huge change or variation in the densities of the air or gas which is processing. So we will definitely categorize it for a particular condition, and or for that particular condition the gas will be considered as incompressible fluid. Well, if we talk about the liquids are considered as incompressible, although the gases majority if the pressure changes they compresses easily. Okay, there is example that if a pressure of 210 atm even we have applied over the liquid, it's only just compressed by 1%. If we talk about the liquid water, if we talk about the gases, on the other hand, we just change a pressure of 0.1 bar, 0.01 atm, and we come to across a change of 1% of the density of the atmospheric air. So there is a huge difference on the behalf of that. Majorly the gas is considered as compressible fluid, and the liquid are considered as incompressible. Okay, now we have studied as well the internal flow and the external flow. Okay, so the aeroplanes, the jet, and the missiles, these are the solid bodies which moves in the air blanket. Okay, so their velocities also impact a lot about the compressibility of the air or incompressibility of the air. Like if the rocket is run and the air is a spacecraft, normal aeroplane runs, so they come across with different types of categories which can be differentiated by Mach numbers. A Mach number is nothing, just a dimensionless number, and it has a ratio of the flow of a speed with the flow of sound, speed of sound, which is equals to 346 meter per second at room temperature. So if the Mach number is equals to 1, we consider that the sonic wave, and if the Mach number is less than 1, this is considered as subsonic. And on the other hand, if the Mach number is become greater than 1, then this is considered as the supersonic. And above to this, we will get hypersonic. Let's consider the example of this. Like normal jets which use for we normally use as to transportation for the passengers. These jets has a Mach number greater than 1. So when they strike the air, they do not compress the air or change the density of the air. But if we move forward from this part to hypersonic side, we have seen a very different behavior. When the air strikes this surface, then definitely compressed up as well because of this high speed. So at that part, we have to consider the fluid as a compressible fluid. On the other hand, for subsonic, we don't need to consider air or gas as a compressible fluid, because, and why I am saying that this is important, because if we consider if we solve a case considering incompressible fluid, it is much easier because its density is not changing from different parts. But if we are supposed to deal with the like hypersonic type of case, here definitely the air which is striking near the solid wall, their density change much higher, and on the other part the density variation is much less. So these things, these scenarios make the calculations much complex. So it is important that if even we are dealing with the air or with the gas, if it is considered that the density is not changing a lot, we consider that fluid as a incompressible fluid rather than considered as a compressible fluid. Okay, then there also a category of flow which we can say as a laminar and turbulent flow. These terms will be demonstrated later on in this semester, and we will discuss it in a very much detailed manner. Okay, but the major, if we see what is the difference between between these two flow patterns. So the laminar flow has the low velocity actually, and the low velocity, what happens, the liquid flow in a proper pattern and do not form any type of rotational flow. So it's just like playing the cards. So the layers is moving one after one and it's not mixing each other. If we increase the velocities and the velocities magnitude up to certain extent, then what happened? Due to greater shear stress, definitely if we increase the velocity amount, it definitely increase the velocity gradient. The velocity gradient increases, which causes the rotational flow in the pipeline. Okay, and the rotational flow, or you can say the eddies formation, come in the liquid or in the flow pattern, which is not like direct flow, that the layer is moving in parallel to each other. In turbulent flow, the layer mix up, we get some rotational flow as well, we get some eddies formation as well. Okay, let's discuss it on the whiteboard as well. Let's consider a pipeline and the liquid is flowing between these two solid layers. Then the layers are moving in that direction. Because velocity is low. But if we increase the velocity much higher, what happened? The velocity definitely, there is certainly intermolecular forces between the layers. So this layer moves with greater velocity, although there is no slip condition. So it definitely hurdles this layer a lot than in this flow pattern, because this flow pattern now have a behavior of this type of flow profile, although this has a flow profile like this. So you can see here the Vmax is much higher than the Vmax here. Maximum velocity of this case is much lower than the velocity maximum here in this case. So what happened? Actually, it drag up the east layers, and when they drag up, this forms some eddy formation, and they show some rotational flow, and due to this rotational flow, the flow becomes turbulent. So we can categorize it. This is laminar flow, which has low velocity, move in the form of layers without disturbing another layer. On the other hand, the velocity is much higher. This is turbulent. Okay, and there are rotational flow can be seen. So here you can easily understand what is the difference between the laminar flow and the turbulent flow. They have arranged ink here, which is open with the wall here. This is the hot reservoir, which need to flow down with this valve. If we open the valve, but we do not allow a lot of water to flow at once from this pipeline, I mean we allow a very much amount of the flow to flow down from this wall. So definitely the velocity here is much less. On the other hand, if we increase the valve opening a lot, then definitely what we comes to see here is the velocity in the pipeline is much higher, and due to which it shows some turbulency in the flow. And on the other hand, if the velocity is low, there is no turbulency in the flow. The ink is moved as parallel as the water is going on. On the other hand, if the flow pattern is turbulent, the ink will mix up all together with all the layers and move flow down to this container. So now another category of the flow is natural versus forced flow. As you can see in the normal routine, we use the equipment like pumps, compressors, in order to move the fluid from one part to another part. And if we are consuming energy in transporting the fluid from one part to another part, this is so called as the forced flow. We mean that we are forcing the fluid to flow in that particular direction. Although natural flow is the flow which naturally flow pattern which a fluid obeys, like the river flow, like if you have a particular amount of water in your home upper tank. So what happened, you just open the faucet and you will get water, because there's no need to forcefully run the water. Let's consider an example. Like this is a pump in which we use electrical energy which converted into mechanical energy, and then mechanical energy is utilized in order to transport the fluid from one part to another part. On the other hand, there is arrangement which is so called as siphon. This siphon is you don't need to consume an extra energy in order to transport the liquid from this part to that part. Okay, let's consider a video as well. Okay, as you can see here, there is a container which full with water, and there is a container which is empty with water. So what they had done is they insert a tube here and then push air from that, so that the air present in this all tube remove from the water or remove from the tube. Then they suck up this up to that much mark, and then let's see what they are doing. They are just placing this tube to the bottom container. But one of the most important factor you need to consider here is that the position of this container must be higher than this container, and the liquid, now you can see here, traveling from this container to that part. But when these both levels become equal, neither the fluid flow from here to this part, or neither reverse flow you will receive. So this is an example of natural flow. You don't need to put an extra effort in order to transport fluid from one place to another place. On the other hand, if we utilize the pumps, compressors, so what we have to do is we are consuming energy in order to move or transport the fluid from one part to another part by consuming the energy, so which is come in the category of force flow. Then steady versus unsteady flow. So what is an steady flow? Let's discuss this thing on the board. Actually, let's suppose this is a process container, mixing container. You are feeding A, you are feeding B, and you are receiving C, which is equals to A plus B, just mixing. Okay, you are homogenizing both these things. And there is an agitator here which is moving in particular direction in order to mix all these both components. So if we consider that this process is at a steady state, so the basic definition of a steady state is dou phi over dou t is equals to 0, and phi is any property. Let's suppose this is a continuous process, so definitely you are watching here the mass flow rate, volume flow rate, the density, the temperature, pressure. Similarly, all these things you are watching for the B. If the values of all these parameters for A and B all together are same from and does not changing with the time, we are categorize it as a steady state. On the other hand, if we see here at this point, what is the rotational velocity? Of fluid? What is the RPM at which this agitator is moving? And what similarly all the mass flow rate, volume flow rate, density, temperature, pressure, every property has the very specific range value. So if it does not changing a lot, it does not changing at all, so we can categorize it in the category of a steady state process condition or a steady state flow condition. But if this is not equals to 0, you are receiving the variation in mass flow rate, volume flow rate, density, temperature, pressure, or any of the thing like RPM or rotational velocity of the fluid, so we can categorize it in the form of unsteady flow pattern.